easy settle is a program where you can determine settlements for multiple load areas, and you can also determine the interactions for neighboring foundations if you want to. And like when you have when you want to build a new building next to an existing building without foundations, you can calculate the interaction from the new load, and you can see the settlements below the old foundations. Then I will show this later. When we create a new project, new one, we have a new project, then we can enter project name. And you can choose a standard here as well. But since the settlement is like a serviceability limit state, there are no partial safety factors. It's always calculated with a partial safety factor with 1.0. So the analysis standard is just you can choose it and it will stand in the output, but it has no influence then on the calculation. Yes. Then we can enter the soil data. Just here. We have a depth groundwater at 100 meters, so it won't have any influence here on the calculation. Then there's the opportunity to enter a correction coefficient kappa. This is not state of the art anymore. It's it belongs to an old standard, so we don't apply any smaller values, and it stays 1.0. Then we have the limit depth here. We the determination, for the determination we use the constraint modulus method. So we divide the stress with the stiffness modulus, and this results in a settlement. And then we add up the settlement over the depth until the load stress is less than 20% of the surcharge stress. This is here. So sigma is less than 0.2 of sigma s, sigma surcharge. So we give a limit here, and then the calculation stops when this limit is fulfilled. Hence, if we continued, we wouldn't stop. If we didn't stop, then the settlement just would get larger than it would actually be. Yeah, and then we can enter the soil layers. For the first example, we would just want to have horizontal layers. The first layer is a sand, which goes to 2.5 meters, has a gamma of 20 and autometric modulus of 120. Then we have a silt layer with a depth at 6.5 meters, a gamma of 21, and a stiffness modulus of 25, which is quite small, in comparison with the sand. And the next, which is gravel, it's the third layer actually goes and has no end, but we just enter 100 meters, the groundwater. It has a gamma with 20 and 150 for automatic modulus. And we say close. Yeah, so we have horizontal layers and you don't see any section here. So yeah, in this program, we just work with a plan view. So not in a section like in Java programs mainly. So we just see the loads from the top. And we want to define a foundation. We have like a rectangle foundation or a circular. We choose the rectangular foundation we have here. We want to have a square one, which is 50 meters and times 50 meters. And then we must choose between the flexible or rigid load area. So like we calculate with the constraint modulus method. So we must define if the load area is flexible or rigid, because we don't use a foundation stiffness. With a flexible load, we have a settlement dip, and with a rigid load area, the bottom of the foundation would stays flat and it does not deform. Yeah, and we choose a flexible load here. Now we define the load. We have point loads, line loads, distributed loads, or circular loads. We choose the distributed loads completely over the foundation. Load case 1, and the load value is 200. Yeah. Then we can also define a section line with this function here. We have a section line and we end with the right mouse key, say OK. So with this section line, you can see the layer thickness then, and the foundation and the settlement line then, or we'll see in the output later. Then, yeah, we can determine the settlement now with the graphic. It just takes a moment. Just takes some seconds when we've calculated. Yeah, now we have the details about the plot image. We can choose between lines and color areas. I will show the lines later. We take the color lines areas now. Say OK. And then you can see now the plot. The brown line is the foundation here. And we can see that we have also like settlements next to the foundation. So it has an like interaction to the surrounding terrain. Yeah, and you can see like we have a symmetric settlement because we have a symmetric load, a symmetric foundation, and we just have horizontal layers. So yeah, this leads to a symmetric settlement as well. And yeah, then we have this function here, where we can like it shows the settlement at the point where we lead the mouse key to. And we have a settlement in the middle of like almost 40 millimeters. And we have a foundation modulus KS of like 5. And yeah, and we can go anywhere here, and it always shows us the specific settlement with the foundation modulus. So yeah, at the edge we have like almost 13 millimeters, and next to the foundation we have like almost like 4 millimeters left. which is like here, 13, yeah. Then we go to the next page where as I mentioned, like this is the section. You can see the foundation with the terrain here, and you can see the interaction, like how much settlement is, which is like left at the surrounding area, and the sediment line at the we have the sediment line close to the to one edge here, so not in the middle. So yeah, the greatest sediment was in the middle. We can edit the bottom depths of the soil layers at like certain points with this function here with the bore points. We cannot change the order of the layers. We can only change the depth. Like the order of the layers must be the same in every bore point then. But we can have different depths of the layers of the bottom of the layers. So we have different layer thicknesses. At least we need 3 points, like 3 bore points. Like the more bore points you have, which are given, the better the results. But we need at least 3 points that we can interpolate the layer thickness between the bore points. So we have, like when we have 4 bore points, which is like here, 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 and here, we end with the white mouse key. Like when we say we have a greater silt layer thickness on the left side, and we have a really small layer thickness of silt at the right side, then it will interpolate between all the bore points, and then we have like different layer thickness all in the area. And this leads to a different settlement, of course, and then we can see the layer thickness later in the section. But first we added the layer thicknesses. We double click on the bore points. This is bore point 1 with greater silt thickness. Sand is just 80 centimeters here. Then we have next is silt, which is like 8.5 meters. Next, gravel, we must not do anything here. We say apply. Then we have the second one. No, we continue with the fourth one because we have here greater silt layer thickness. Sand is 1.2 meters here. Then we have the silt, which is 12 meters here. Okay, apply. Then we have the second one. And here we say we have a greater sand thickness, which is like 3 meters. And then we say we have 3.9 meters, the bottom edge. So we have 90 centimeters silt. Say apply. And the third one is sand with 4.3 meters. And the third is just 20 centimeters. So we have 4.5 meters. Apply. So we have different layer thickness, and we see this now in the graphic. Oh, we must save it. 20. We can choose between lines and colors. We choose the colors. So now, yeah, you can see that we have more settlements on the left side where we have a greater silt thickness than on the right side where we have like a very small silt layer thickness. And we have here in the middle almost like 53 millimeters, which is really like much more greater than before. And here over here we just have like 50 millimeters left. So yeah, when we go to the second page, you can see this here. This is like the layer lines, yeah, the interpolated ones, and the settlement line here. And we have really great, really large settlement here, 43 millimeters. And you can see like that we have on the right side, like less sediments left. Yeah. Yes. So we have a not symmetrical settlement here caused by the different layer thickness. So yeah. Yeah, when we go to the results here, you can see the settlements for each foundation edge, and you can see the maximum settlement where it is, like the coordinates, and yeah, it's like 52 millimeters, and you can see the foundation modulus. The foundation modulus is the settlement, the stress, the maximum, no, sorry, the stress divided by settlement, this direction, yeah. Yeah. As I mentioned, we can also see the interaction from a load to a neighboring foundation. So we want to have a small foundation here at the right side. We have a rigid one here, and we don't enter any unit weight gamma because you just want to see the influence from this load here on the small foundation, so we don't put any load on it. Say okay. And then we have the section going through the foundation. So this is works well. So we go back to the plot image. And then we can see the foundation here. And when we see the settlements, so we have like almost 4 millimeters at this edge, and we have like 1.5 millimeters at the other edge. So this foundation will incline then, but this settlement is just from this load over from the greater foundation. Yeah, so we just see the influence from the neighboring load. Then we can set the plot images, like the details. We can either choose between lines and colors. We can also say that we want to change the details. We can either choose between the number of colors, like we have 16 colors right now, or we can say we want to have a spacing. So the spacing, which is like done automatically right now, yeah, like it's really hard to read the settlements now from the graphic. So we will say we want to have like a spacing of 2 millimeters, that makes it easier. And yeah, so we say okay and okay. So it's like smoother now, like more colors, but it shows like more the different, like the settlement, how it like grows or like increases or decreases. Yeah. Or we can choose the lines over here, and we can say, we can see the lines also like in colors, but with each line, like almost like each line, we have like the number next to it, so it makes it like more easier to read out the settlement from the graphic. Yeah. Then we can we go back to the input window, and the section lines you can draw freely. So like, for example, you can start here, going down through the other foundation. So you will see the settlement at this top edge of this the first foundation. Then you can see the settlement next, like in the terrain, and then you can see the settlement in the other direction from the smaller foundation, which we can see in the graphic then. Second section, this is the first section, this is the second section. You have the settlement line here, and you have a small settlement in the terrain, and a settlement below the smaller foundation. Yeah. Then I want to show you that we can also, I want to go back to the results here, because I want to show you here the settlements again. For the second foundation, we have the settlements shown here, but we have no foundation modulus here because we have no load on top of the second foundation. Yeah, so we cannot like calculate like some the foundation modulus because we have no load, but we have settlement. But yeah, it's not working. Then we go back to the input window. The last function I want to show you is the evaluation points. So you have there's a separate plot rate in the results. Then we set one evaluation point in the first foundation and the second one here in the second foundation. And when we go back to the results, so this is the separate plot. You can see the surcharge stress at the left side, which increases with the depth. And then you can see the load stress at the right side, which decreases with the depth. And like what I explained before is that we have this limit when the load stress is less than 20% of the surcharge stress, which is like at a certain depth, and this certain depth is shown here, the applied limit depth, which is like almost 16 meters underground. And then like the calculation stops. Then you have like this load stress divided by the stiffness modulus of the layers leads to the settlement, and the settlement is like added over the depth together. So you have a complete settlement over the depth, and this is like shown settlement in the results. Yeah. Then at the second point, you have this surcharge stress, but we always use the same limit depth. Then we can compare the results, like the settlements. And you can see here that the surcharge, like the load stress, increases with the depth, which is like different from here. So like here it starts like with 200, which we have entered, and here it starts with 0. So you just can see the interaction from the neighboring load. And this load stress divided by the stiffness modulus is the settlement below the second foundation then. So these are all the functions we have in DC Settle.